Welcome to Candies and Fudge. We'll discuss all the different ways we can incorporate the sweet sugar and perhaps some other ingredients into tasty candies. Let's get started. Candies can be divided into three main groups: crystalline candies, non-crystalline candies, and candies whose texture is modified with gums, gels, and pastes. In practice, however, there is overlap between these groups. For example, caramel can be either crystalline or non-crystalline. The image on the left shows non-crystalline caramels, whereas the image on the right shows crystalline caramels heated to different temperatures, and thus the extent of caramelization of the sugar varies. Hard candies, such as the ones shown here, are non-crystalline. These include hard drops, clear mints, butterscotch, bonbons, lollipops, and more. Hard candies are made by boiling the sugar syrup until the cooled syrup will contain only 1 to 2% water. The syrup is then poured onto a surface and cooled down. During the cooling process, the syrup is kneaded with colors and flavors in much the same way that bread dough is kneaded. This kneading mixes the colors and flavors throughout the viscous syrup. Once the syrup cools, it solidifies into a hard candy that holds its shape. The sugar, that is, the sucrose, will tend to crystallize, so corn syrup, remember this is glucose dissolved in water, is added to prevent the crystallization. Now, by crystallization here, I mean the process of forming large crystals with a well-defined structure at the molecular level. That well-defined structure causes crystals to have particular shapes with large, flat sides and sharp edges, similar to what you see in cut gemstones. But the glucose and water molecules break up the well-defined structure of the sucrose molecules, so the result is an amorphous structure with no clearly defined faces and edges. That is, a transparent sugar glass results. Because of the amorphous structure, we can heat the sugar glass and form it into a variety of different shapes. If the structure were crystalline, it would break into pieces rather than bend when heated. The development of crystals of sugar in the candy is generally considered a defect in hard candies. But there are some exceptions, as crystals are intentionally formed in some candies such as candy canes and the white, non-transparent mints we often find given out at restaurants. These crystals make it easier to break the candy with the teeth. As force is applied to the crystal, it shatters along a specific plane rather than bending. That is, the crystal's plasticity is quite low. Cotton candy is made by melting sugar and then forcing it through tiny spinnerets into the air, similar to how a spider forms the thin strands of its silk by forcing a liquid through spinnerets. When the melted sugar meets the air, it quickly cools and hardens into an extremely thin strand. When that strand then encounters the water in our saliva, it almost instantly dissolves, making the cotton candy fluff seem to disappear. Another type of candy is brittle, such as peanut brittle. Brittles are low-moisture candies that include butter and milk solids and generally also pieces of nuts. The fats and proteins from the butter and milk absorb light and so make the brittle opaque. During the cooking process, browning reactions or Maillard reactions between the proteins and the sugars make the candy quite brown. Now let's turn to caramels, toffees, and taffies. These candies are generally non-crystalline candies that contain milk fat and milk solids. Like the brittles, the addition of these milk fats and proteins means that they'll be opaque and brown from Maillard reactions. They are chewy instead of hard because of the milk fat. As we chew them, the pressure squeezes small droplets of fat out from the sugary mass, and so they have an almost melted, mouth-watering texture similar to chocolate. These candies are soft and chewy due to their higher water content than that for hard candies, their high corn syrup content, and the presence of casein proteins from the milk. The characteristic caramel flavor comes from browning reactions between the milk proteins and the sugar. We've talked about these Maillard reactions a number of times before, including when we discussed cookies. Shown here is an image with a sugar syrup heated to progressively higher temperatures and consequently developing darker and darker brown coloring due to the products of Maillard reactions. Now, we mentioned earlier when discussing hard candies that the sugar syrup forms a glass-like solid. And like glass, we can heat it up to make it soft and pliable, which means that we can use a variety of techniques similar to what would be used in glass blowing, to create a wide variety of different shapes. We can roll it into flat ribbons that we can then bend and form into bows. We can form bubbles or holes in it to create structures that would look like mesh or coral. We can add a variety of dyes to add different colors, and we can melt small portions and then allow them to cool to effectively glue various pieces together into a larger work of art, such as that shown with the dolphins on the right. We've already discussed non-crystalline candies, so now let's turn to crystalline candies. The simplest of the crystalline candies is rock candy. To make rock candy, cook a sugar syrup to the hardball stage, pour it into a glass, put in a toothpick to serve as a removable scaffold on which the sugar crystals can grow, and allow the sugar crystals to slowly grow over the course of a few days. After a brief wash in cold water and allowing them to air dry, the rock candy crystals are ready to eat. Now, why do we need to wash in cold water? A quick wash in cold water allows you to wash away any impurities on the surface of the crystals without significantly dissolving the crystal itself. If you were to use warm or hot water or a longer wash time, much more of the crystal would dissolve. Now, where the intent of rock candy is to form large crystals, such large crystals are quite hard, so chewing them is difficult. When we eat rock candy, we tend to slowly suck on it similar to how we would with a lollipop to allow time for our saliva to slowly dissolve the outer layers of crystallized sugar. But for most other candies, we want to be able to chew them, so we need to break up these very large, difficult to chew crystals into a much larger number of much smaller crystals. Within each individual crystal, we'll have to bite just as hard to break it apart. But we don't need to break each individual crystal. Instead, we only need to separate one crystal from its neighboring crystals, and that can be much easier to accomplish with far less chewing force if we keep those crystals small. Fondant, from the French word fondre, meaning to melt, is the base for many candy creams that are used as the flavored fillings in many chocolates. In the typical box of chocolates, you might have some chocolates filled with caramel fillings, but most of the remaining fillings will have a fondant base to which a variety of different flavors have been added. But fondant can also be used as icing on cakes. It is quite useful in this regard because it can be rolled into a smooth sheet and then molded onto the cake, giving the cake a seamless coating that we can shape in a variety of ways. Its texture is somewhat similar to Play-Doh, so we can sculpt a variety of shapes from fondant and gently press them onto the fondant cake surface to get them to stick. Most people find the taste of fondant pleasant, but less appealing than a traditional buttercream icing, so the fondant is often used to provide decoration on the outer surface of special cakes, like wedding cakes, while the icing between the layers of cake is typically the more traditional and tasty buttercream. Another crystalline candy is fudge. Now, we can think of fudge in two different ways, either as a fondant with added milk and fat, and sometimes chocolate, or as a crystallized version of caramel. Both fondant and fudge are made with corn syrup, which helps to form the many small crystals that prevent the growth of a few very large crystals that would be difficult to chew. After boiling and then cooling to between 100 and 130 degrees Fahrenheit, the mixture is beaten for about 15 minutes until crystallization is complete. This beating also helps to prevent the formation of large, difficult to chew crystals by breaking up any larger crystals that do happen to form. The final texture of fondant and fudge depends heavily upon moisture content. A difference of just 1 to 2% is significant. If it's too dry, the texture will be dry and crumbly, like the image on the left. If it's too moist, the texture will be soft and perhaps even runny and will appear shiny due to the syrup between the crystals, allowing the mass to slowly flow. If you're making the fudge for this week's experiment, don't be discouraged if it turns out a bit dry or wet. Simply adjust how long you let the mixture boil for the next time. Hard panned candies have some sort of center, generally a nut or a spice, but also sometimes chocolate. That center is rolled around a hot pan and periodically sprayed with a concentrated sugar syrup. The heat causes the moisture to evaporate, leaving behind a hard, thin layer of crystals. As this process continues, these crystals build up to form a thin candy shell coating the center. We'll often add a variety of different colors to different batches of hard hand candies, and then mix those batches together to make a colorful mix of candies as you see in M&Ms. Okay, now let's turn away from crystalline candies to the third category of candies, those whose texture is modified with gums, gels, and pastes. Aerated candies like marshmallows and nougat have a light, chewy texture and are made by combining the sugar syrup with an ingredient that forms a stable foam. Egg whites, gelatin, and soy protein are the common foaming agents. We've already discussed in the video on meringues how egg whites form stable foams, so we're not going to get into how to form the foam here. Marshmallows were first made in France from the root juice of the marshmallow plant. Like their name suggests, the marshmallow grows naturally in marshes. The marshmallow root juice was mixed with eggs and sugar and then beaten to form the foam. Today, marshmallows are made by combining a viscous protein solution, generally gelatin, with the sugar syrup and whipped into a foam. The gelatin produces an elastic structure, whereas egg whites make a marshmallow that is lighter and softer. That is, when you press into a modern marshmallow produced with gelatin, it will deform, but then it will bounce back once you stop pushing into it. A marshmallow made of egg whites will more easily deform, and it won't bounce back to its original shape once your finger is removed. We have a wide variety of other candies in this category, including marzipan, Turkish delight, licorice, jelly beans, and gummy candies of various shapes and flavors, some of which are coated with a powdered or crystalline coating that modifies their texture and perhaps flavor. One such example is in candies like Sour Patch Kids, where the coating contains citric acid to make that outer coating taste sour. These candies are made by mixing a sugar syrup with starch, gelatin, pectin, or plant gums, and then allowing the mixture to cool into a dense, chewy mass. Often, the texture is poured into molds prior to cooling. Once removed from the molds, the candies are flexible but still retain the shape of the mold. The chewing gum that we chew on today is a quintessentially American candy, but humans have chewed gums, resins, and latexes for thousands of years. These early gums were derived from various plants. The Greeks used the resin of a pistachio tree. Both Europeans and North Americans used the resin of a spruce tree. The Mayans used chicle, the latex of the sapodilla tree, and Arabs used acacia, which is now known as gum arabic. Whatever the source of the flexible plant material, its plasticity and elasticity allow it to be chewed for long periods of time. We've since moved on from these natural, plant-based gums, and so modern chewing gums are mostly made of synthetic polymers such as styrene butadiene rubber, which is also used in car tires, or polyvinyl acetate, which is also used as an adhesive and an additive in paints. These polymers exist as long, flexible chains of monomer units linked together, and their strong bonds mean that we can chew them for far longer periods of time before they degrade. Despite being man-made, these polymers are safe to chew and even swallow. The large polymer molecules aren't broken down by the digestive system, so they simply pass through you largely unchanged. There's no harm in swallowing gum, as any portion that isn't digested will pass along with the rest of the undigested food you eat and leave your body in 2 to 5 days. So how should we store our candy? Candies generally contain very low amounts of water and high concentrations of sugar. Like we saw with our jams and jellies, this high concentration of sugar generally dries out any microbes, so candies rarely spoil by microbial growth. Instead, the candy flavor will slowly degrade over time as the fats oxidize, turning them rancid similar to how meats turn rancid. This process can be slowed by refrigeration, but be careful to wrap the candy tightly to prevent condensation on the candy surface. Condensation will lead to a condition called sugar bloom, in which the sugar crystals dissolve in the condensed water and then deposit as solid sugar crystals once the water evaporates. These crystals will usually be significantly larger than the sugar crystals in the original candy, and so they'll significantly alter the texture of the candy. As we saw in an earlier video when we discussed chocolate, the fat bloom largely occurs when the candy gets too warm and the fats rise to the surface. Those fats then recongeal as the temperature drops below their melting point. This often causes the chocolate to feel greasy, but it will also speed up the oxidative rancidation of the fats since they'll have much more exposure to oxygen in the air.